All right, today's topic is acid-base balance during exercise. We've touched on it a little bit in a previous chapter. We talked about the respiratory system. Now we're going to focus right on acid-base. It's a short chapter, but there's some really interesting things in there. So let's get right into it. Here's a quick outline of topics that you can use as a guide as you're studying later on going through the chapter. So acids and bases. For our purposes, we're going to define an acid as a molecule that can release hydrogen ions into solution. So you dissolve it, hydrogen ions come out, or you form it, hydrogen ions are released. What we mean by acidity is an increase in the concentration of hydrogen ions. So lactic acid, when it's formed from pyruvic acid, releases hydrogen ions into the surrounding solution. So that's why it's called an acid. Then you have lactate. You may have noticed that we kind of interchangeably use lactic acid and lactate. Oftentimes that works fine, but what we really mean is we form lactic acid from pyruvic acid and it releases a hydrogen ion forming lactate. A base is just the opposite. It's a molecule that's capable of taking a hydrogen ion, binding a hydrogen ion, and taking it out of solution. And that'll become important when we talk about buffering. So we'll come back to that. But bicarbonate ion is an important base in the blood. It's the important buffer of the blood because it can take up the hydrogen ions that are produced by processes like formation of lactic acid. pH is a way of expressing the hydrogen ion concentration, but it kind of makes things a little bit confusing. pH is the negative log of hydrogen ion concentration. And the upshot of that is, the way the math of logarithms and the negative log works is, that's the same thing as saying the log of 1 over hydrogen ion concentration. The negative sign is like looking at 1 divided by hydrogen ion concentration. The reason I'm bringing that up is so that when things become more acidic, when hydrogen ion concentration goes up, pH goes down. So a more acidic solution has a lower pH, and a more basic solution has a higher pH. So just remember that, it's just opposite. High hydrogen concentration, low pH. The body pH is right around pH 7, what we call neutral pH. So your body pH is around 7.4. Your blood pH is kept right around 7.4. Even small changes that occur in your body, such as going from 7.4 to 7.2, say, that is more acidic, or 7.1 or even 7. Things don't get a lot more acidic in your blood than that, and things don't get much more basic than say 7 point, below pH 8 anyway. So adding hydrogen ions, increasing concentration means lower pH. These numbers are going down, and becoming more alkaline, lower hydrogen ion concentration, the pH numbers are going up. So again, here's your body, your blood pH is around 7.4 all the time. If we make things a little bit more acidic, it's going to drop a little bit, say to 7.3, maybe even 7.2, but not much more than that because there's a very narrow range of pH for survival. I don't know if you remember from way back in the beginning when we talked about metabolism, we said that all the enzymes that catalyze every single reaction in all your cells, including all the making of ATP and oxidizing fuel molecules and the cross-bridge cycling, all those things depend on the pH. All those proteins, if the pH goes out of range, will no longer function. The cell would die. Small changes of pH in the muscle cell affect performance. Fatigue arises in part from acidification of the cytoplasm. So, excuse me. So how can your pH become more acidic? Well, the most obvious thing is you can add some hydrogen ions, and now the pH starts to go down. Things are more acidic. pH is dropping. If that happens in your blood, that's called an acidosis. If the pH isn't 7.4, we say you have an acidosis. But interestingly, if there is a base chemical that's normally in your blood, something that can take up hydrogen ions, and it's taken away, that's the same effectively as adding acid. So taking away base is like adding acid, and you'll have an acidosis. How do you get an alkalosis, a rising pH? If you lose acids out of your body, then you'll have lower hydrogen ion concentration and alkalosis. We'll see in a quick example of that. That's not so important for exercise. In exercise, when we have pH changes, they're largely increasing hydrogen ion concentration by adding hydrogen ions in the form of lactic acid, for example, and a couple of other things. The term metabolic acidosis refers to an acidosis, a dropping blood pH and body fluid pH that's not caused by something wrong with the way the lungs are performing. In other words, when you add lactic acid to the blood and the pH starts to go down, that's called a metabolic acidosis. If it was something wrong with your respiratory system, it would be called a respiratory acidosis. If you had like emphysema, you would have a respiratory acidosis, but in this case we're talking about metabolic acidosis, lactic acidosis. Just a couple of other quick examples. If you are starving, you will start to be forced to burn a lot of fat. High amount of fat metabolism in excess of just the amount we eat in our diet, but forcing you to do a lot of fat metabolism because there's just not carbohydrates coming in, then you'll form ketone bodies or keto acids in your liver, and you'll have a drop in blood pH. It's called ketoacidosis. It's like the overdone version of a keto diet, right? When you have a keto diet, you're producing some keto acids, but hopefully not enough to actually cause an acidosis. But that's what would happen if you really went overboard with your keto diet. Uncontrolled diabetes, same thing, affected starvation. No carbohydrates are available in the cells, and therefore your liver starts making ketone bodies. So those are analogous situations for different reasons. Severe diarrhea just so happens that you'll lose bicarbonate ion, the base of your blood, and if you lose that extra bicarbonate ion, that's equivalent to adding acid. Losing base is the same thing as adding acid, not acidosis. Metabolic alkalosis, rising pH, if you lose a lot of acid from your body, that's the same as adding base effectively. So if we lose hydrogen ions, lose acid from our stomach, your stomach is like a seething cauldron of acid fluid. If you'll get rid of that from your body repeatedly, then your blood pH is going to start rising. You'll have an alkalosis. Some kidney diseases are associated with alkalosis. So let's just quick look at, this is an important thing. 3 sources of hydrogen ions, 3 sources of acid during exercise. Number 1, we already looked at this chemical reaction when we talked about the respiratory system. We produce carbon dioxide in the tissues, right? Metabolism to produce energy, and the carbon dioxide can be combined with water to produce carbonic acid. I left out the middle step this time. Carbonic acid, that requires the activity of carbonic anhydrase enzyme, and then that carbonic acid can dissociate, producing hydrogen ions and bicarbonate ions. So there's our acid component. More CO2 in the tissues means that the blood in the tissues, the fluid in the tissues, is slightly more acidic, and that helps us, we said, dissociate oxygen from hemoglobin. Lactic acid, very familiar. We've been talking about that since the very beginning. During anaerobic respiration, during high-intensity exercise, we're forced to do anaerobic glycolysis with fermentation, producing lactic acid. Lactic acid dissociates, releasing hydrogen ion. During cross-bridge cycling, interestingly, ATP hydrolysis, breaking that ATP to release the energy to reset the cross-bridge in order to do another cross-bridge cycle, releases hydrogen ions. So as you're powering through bazillions of cross-bridge cycles under muscle contraction, you'll produce a lot of hydrogen ions that need to be dealt with in your body. So here's just, as you know, familiar, our authors like to put box flow diagrams sort of as another way of instead of looking at a lot of words on a page, looking at 3 things that produce hydrogen ions during exercise. Anaerobic metabolism produces lactic acid by fermentation, hydrogen ions. CO2 production in the working muscles, lots of CO2 is going to be converted to carbonic acid, and then it dissociates, producing hydrogen ions. And cross-bridge cycling involves, and other cellular activities involve hydrolysis of ATP, releasing that energy, and hydrogen ions. So boom, typically, in a given day, we have a net excess of acid that the body needs to deal with. So again, as you're doing high-intensity exercise, producing a lot of lactic acid, lactic acid releases hydrogen ions. The more intense you are exercising, the more lactic acid you're going to produce. And this part of this PowerPoint, the author just wanted us to take a look at and consider different sports and the activities that are involved in those sports, and how likely are those activities in those sports to push us in that way that we're doing this high-intensity lactic acid producing exercise and producing acidosis, which will cause us to fatigue. We know that acidosis can affect muscle contraction and performance. So here's a list of familiar activities that we all enjoy, at least maybe most of them until we get down here maybe to the bottom. But if you start getting into intense exercise where you're pushing it out for a longer period of time, right? We know that sprinting, of course, you might be like, why is sprinting here with low risk of acid-base balance or disturbance? It's because, as we'll see later, your body can accommodate the amount of lactic acid that's produced when it goes into the blood. So the pH of the blood is not really going to change much after a 100-meter sprint. Now, inside those type 2X muscle cells, it will be, but not in the blood. So we don't actually develop an acidosis. If we keep on like pushing in that same way where we're doing anaerobic metabolism for a longer period of time, then that lactic acid is going to accumulate in the blood. We're going to have lactic acidosis, and it's going to affect our entire body and fatigue. So getting down into more and more longer duration activities, right? We were getting into longer duration and getting more and more acidosis, but now we're starting to go the other way. As you get into longer and longer duration activities, now you're forced to back off and do submaximal exercise, less intense exercise, more aerobic respiration, more type 1 fibers are being recruited. And so for the 10,000-meter run, the marathon run, we're not producing very much lactic acid. And so we can do this for a run for a long time at that submaximal rate and not produce this much lactic acid. Buffers. A buffer, as we said, is much like when we talked about bases. A buffer is a chemical that can take up hydrogen ions or release hydrogen ions. So buffer isn't just considering that one thing. Buffers are chemicals when dissolved in solution can either take up excess hydrogen ions or release them when there's a vacuum of hydrogen ions, a drop in hydrogen ion concentration, so that the pH of the solution doesn't change. They control the pH. They keep the pH from changing, even though we're going to try to disrupt it by adding, say, hydrogen ions. In your blood, the primary buffers are two things. Bicarbonate ion, there's 24 millimolar bicarbonate. That's a lot. It might not sound like anything, but that's a lot of bicarbonate ion in your blood. So as we add hydrogen ions from, say, lactic acid, they can combine with bicarbonate, be converted to carbonic acid, as we learned in the respiratory system, and breathed out as CO2. So that's a very important buffer. It's called an open-ended buffer because we can keep breathing out CO2 and keep adding acid combined with bicarbonate until we eventually run out of bicarbonate. And then we'll start having real acidosis. The blood proteins and hemoglobin in the red blood cells, all those proteins, that's a high concentration of proteins, and it turns out that proteins can gather up and mop up hydrogen ions to quite an extent. So that's another important buffer in the blood. Cells. Inside of cells, there's a lot of protein in the cytoplasm, so proteins are important intracellular buffers too, but there's also some bicarbonate in there, some hydrogen phosphate, some other buffers inside of the cells. All that brings us to an interesting point. Well, if lactic acid produces fatigue and acidosis, when the blood pH starts to go down, we have a lot of lactic acid, for example, that's going to make us fatigue. What if we could put some extra buffer in there? We said there's 24 millimolar bicarbonate in the blood to start mopping up some of those lactic acid hydrogen ions. If you eat baking soda, sodium bicarbonate, appropriate interval before an intense anaerobic activity, then you actually, it's been demonstrated, you can actually reduce that, delay that acidosis and just give you an edge, increase your performance before you fatigue. So it's an actual finding. So if you can tolerate eating baking soda, which most people are not super fond of that, it'll make you feel a little nauseous oftentimes, but it's an actual functional way to stave off fatigue from lactic acidosis temporarily. So we'll have one more section to talk about some more aspects of acid-base balance during exercise in part 2 of chapter 11 of our exercise physiology text.